Today we introduce uncertainty. In this game, player 1 moves first and picks A or B. But when player 2 moves, he doesn't know if he's here or here. What this circle means is you know that you're in this circle, but you don't know where. So if you were playing this game with another person, what would happen is player 1 would first move, would secretly write down A or B, then say, player 2, your turn. Player 2 would move without knowing whether A or B has been played. Then both parties would reveal and they'd end up, you'd see where they were. Now notice I gave these two the same name and these two the same name. That's because player 2 really only has two choices. Player 2 can't do something different if he's here versus being here. Obviously it would be a dead giveaway if I label this X and Y and this, say, L and M, because then if you were choosing between L and M, you would know that you were right there. So I need to give these the same name. So why don't you pause the video and figure out what you think is going to happen in this game. Okay, so I think the way to solve this game is to recognize that X is a dominant strategy for player 2. Let's see why. Now, when player 2 gets to move, player 2 will say, I don't know if I'm on the left or the right. I don't know if I'm here or here. Now, if I were here, I would know that X is better for me than Y. And if I were here, I would know that X is better for me than Y. Oh, wait, I guess I should pick X. So I have uncertainty, but no matter how that uncertainty works out, I'm always better off with X than Y. So X is a dominant strategy for player 2, meaning it's better no matter what player 1 happens to have done. Player 1 will figure this out. Player 1 will say, okay, player 2 has a dominant strategy of X. So I'm going to count on player 2 always picking X. So if I pick A, I get 7. If I pick B, I get 0. Well, I'm going to pick A, and the parties will end up here. Now, it's important when solving this game to circle both X's. That's because player 2 isn't just playing X if he's on the left. He's playing X unconditionally. He has to. Player 2's choice is either to circle both X's or both Y's. Now, this game is functionally the same as the game of where you move simultaneously. Because even though player 1 is moving first, because player 1 isn't really telling player 2 what player 1 did, it doesn't practically make much difference if they move simultaneously or if they move sequentially. And so you can say it's basically the equivalent of this game where you would see the parties would end up here because X is a dominant strategy. Because, again, player 2 would say, well, look, if player 1 is going to write down A, I'm better off with X than Y, and if player 1 is going to write down B, I'm better off with X than Y, so X is a dominant strategy, I'll always play X. Player 1 would say, given that player 2 is going to play X, I'm better off with A than B, and the parties will end up here, for pretty much the same reason that they did in the game where it's sequential. Okay, let me give you a new game, sequential game with uncertainty. Please pause the video and try to figure out what's going to happen. And I would urge you really do pause the video, especially if you're taking a game theory class for a grade that you care about. All right. Now, I think we can solve this game by recognizing that A is a dominant strategy for player 1. See, player 2 cannot condition her move on what player 1 does. So when player 1 is writing down A or B, player 1 will say, if player 2 is going to pick X, he's going to pick X regardless if I picked A or B, and the same with Y. So player 1 will say, my move of A or B can have no effect on what player 2 is going to do. Now, it's true what player 2 thinks player 1 is going to do will affect what player 2 does, but that's different from what player 1 actually does. So player 1 will say, all right, I don't know what player 2 is going to do. But what if somehow I knew player 2 was going to pick X? Well, if I knew player 2 was going to pick X, I would prefer to do A, right? If I knew, someone tells me, I definitely know player 2. Player 2 is all for X. Well, I would go with A because 5 is better than 3. And similarly, if someone were to tell me, I know player 2 is going with B. I know player 2 is going with Y. Well, if I knew player 2 was going with Y, player 1 would also rather have A than B. So because this number is greater than this number, and because this number is greater than this number, A is a dominant strategy for player 1. Now, player 2 will realize that. Player 2 will say, player 1 has a dominant strategy of A. So I bet player 1's going to pick A. So even though I can't see where I am, even though I'm told you're somewhere in this oval, I'm going to believe I'm on the left. And if I think I'm on the left, I'm going to go with X. So player 2 will circle both X's, and the parties will end up right here. Now, in the games with certainty, recall we solve them by going backwards. We can't do that with this game because player 2 doesn't know if he is here or here, so we can't use the backwards approach we used in past games. This game also has an equivalent of a game where you move simultaneously, you move at the same time, and it's this. And you can see here, A is a dominant strategy. Player 1 will say, well, look, if player 2 is going to write down X, I'd rather be at A than B. And if player 2 is going to write down Y, I'd rather be at A than B. So A is a dominant strategy. And player 2 will realize A is a dominant strategy. Player 2 will realize that player 1 is going to play A. And given that player 1 is going to play A, player 2 is better off with X than with Y. All right, let me give you another game. In this game, there is no uncertainty. So why don't you solve this? Pause the video and solve this game. All right. So this one we can solve just by going backwards. Player 2 were here. Player 2 would say, well, 11 is better than 5, so I'd go with M. And player 2 would say, if they end up here, 40 is better than 7, so I'm going with X. Player 1 will take this into account and will say A leads to M, which leads to 9. B leads to X, which leads to 30. So player 1 will play B, and the parties will end up here. Now what I want to do is keep the game the same, except I'm going to add uncertainty. So I'm going to add uncertainty, and I'm going to have to change variable name. I'm going to have to change the branch names to make these the same and these the same. All right. So I've added uncertainty to the game, but otherwise I've kept it the same. Please pause the video and take a guess as to what you think is going to happen. All right. Here is what I think is going to happen. Now, A has become a dominant strategy for player 1. Remember, player 2 can't condition his move on what player 1 does. So player 1 would say, well, player 2 is going to pick L or M, and what I write down won't influence that. If player 2 is going to go on to pick L, then I would rather have A than B. If player 2 is going to go on to pick M, well, I'd also rather have A than B. So A is a dominant strategy for me, so I'm picking A. Player 2, now player 2 doesn't have a dominant strategy because if player 2 somehow knew she was here, she'd prefer M to L. And if player 2 somehow knew she was here, she would prefer L to M. So player 2 will say, I can't on my own decide what to do. I can't decide what to do just looking at my payoffs. When you have a dominant strategy, that means you can decide what to do looking at just your own payoffs. So player 2 will say, before I know what I want to do, I have to figure out what player 1's going to do. Oh, but wait, looking at player 1's payoff, I realize that player 1 has a dominant strategy of A. That means even though I don't see whether I'm here or here, I can infer that when I move, I'm here. And if I'm here, I want M. So the parties will end up here. Now notice when I didn't have the uncertainty, the parties ended up here and they were both better off. So really, how did that happen? I mean, why can't the parties end up here? Let's imagine the parties talk about this. So, they do the game with certainty, or they see with certainty they could end up here. Is there any way they could talk? Could player 1 say, hey, look, player 2, I'm going to play B and then you play L and we'll just end up here. We'll both be better off. Will player 2 believe that? Unfortunately, no. Because let's imagine player 1 and player 2, they talk and player 1 says, I promise I'll play B if you promise to play L. Well, player 1 would have an incentive to break his word, right? Because imagine player 2 keeps his word, player 1 would then be better off playing A over B. So if player 1 cannot credibly commit to playing B, player 2 will expect player 1 to play A and will play M. What the uncertainty would do, if we remove this uncertainty, player 1 could commit to play B by just playing B, right? Player 1, if there's no uncertainty, will play B. Player 2 will see that player 1 played B and will know we can't change his mind. And if player 1 plays B, player 2 is better off playing L, and they'll both end up here. Unfortunately, while there's uncertainty, player 1 would love to convince player 2 that he's played B, but even if he convinces player 2 that he's going to play B, he has an incentive to lie and play A. Player 2 will take into account that player 1's promise to play B is not believable, so we'll believe that despite what player 1 says, player 1 really played A, and player 2 will think when he gets to move he's really here, and so the player 2 will respond with M, and the parties will end up right here. Thank you very much.